Today we will discuss about the conservation of angular. Before discussing what is angular momentum conservation, we will discuss shortly about angular momentum and torque, though you are already familiar with these topics in your higher secondary classes. So you know what is linear momentum. So the angular momentum is defined as the moment of linear momentum, which is represented by the letter J, which is equal to R cross P. Where P is linear momentum, which is mv, so we can write n into R cross V, where R is the vector distance of the particle from that point about which the angular momentum is measured, and P is equal to mv is the momentum in an inertial frame in which the point is stationary. So, definition of angular momentum. Angular momentum is a vector quantity whose magnitude is given by real sin theta is equal to the product of linear momentum and its perpendicular distance from the reference point. Since the definition is R cross P, the magnitude can be written as Rp sin theta or PR sin theta. So the magnitude is equal to, we can say, the product of linear momentum. Linear momentum is P, and the R sin theta from the reference point, that is the point about which the measurement is done. Its direction is perpendicular to both R and P. Since the definition is R cross P, so the quantity angular momentum will be perpendicular to both R and P. The component of J along any line or axis passing through the fixed reference point is often called the angular momentum of the particle about this axis. So the component of J along any line or axis passing through this fixed point, that is the reference point, is called the angular momentum of the particle about this axis. SI unit of angular momentum is kilogram meter square per second or joule second. Okay. Now for J is equal to m into R cross V, which can be written as m R square omega. Since V is equal to R omega, we can write this as m R square omega. Its magnitude J is equal to m R square omega, which is nothing but mvr, since R omega is V. Hence, J and omega are along the same direction and are perpendicular to the plane of the circle. So, differentiating J with respect to T, we will get dJ by dt is equal to d by dt of R cross P. That is, differentiating this term by applying the product rule, we will get dr by dt cross P plus R cross dP by dt. In the term dr by dt cross P, P is equal to mv and dr by dt is V, which is position vector. So differentiating with respect to time will give you velocity, and P is cmv. So d by so vector product of V cross mv. M is constant, so this is m into V cross B. Vector product of same product is 0, so this term will converge to 0. So the first term is 0 here. So we will get R cross dP by dt. dP by dt is nothing but the rate of change of momentum, which is force according to Newton's law. So this is the force applied on the particle. The vector product of R and F is called torque or moment of force about the reference point and is represented by tau. So here we get, when differentiate the angular momentum with respect to t, the result is r cross p. This is nothing but the moment of the force applied to the system. This is known as torque, which is represented by the letter T. Some book may refer this symbol as tau. That is tau instead of T. You can represent any letter T or tau, but the meaning should be purposeful. Okay. So the torque can be defined as torque T is equal to dj by dt, which is equal to r cross F. Okay, thus the torque is equal to the rate of change of angular momentum. So it is simply the rate of change of angular momentum. So its unit is Newton meter. Now the angular momentum of a system of particles. If a number of particles are moving independently or attached to one another in the form of a rigid body, then the angular momentum of the system about any point is defined as the vector sum of angular momentum of separate particles about the same point. So this is about the system, a system consisting of a number of particles. So the angular momentum of a system of body about any fixed point is equal to the vector sum of the angular momentum of individual particles about the same point. This is quite general, just as in the case of linear momentum. Now, if J1, J2, etc. are the angular momentum of various particles of the system about a given point, the total angular momentum J of the system about the point is given by the sum of individual angular momentum about that same reference point, that is J1 plus J2 plus etc. Here J1 is equal to R1 cross M1 V1. J2 is R2 cross M2 V2 etc. individual angular momentum. So this is not J1, this is J simply, and this is J1, this is J1, this is J2 etc. So in the summation form we can write J as J as summation over n is equal to 1 to n Rn cross MVN. MVN is nothing but Pn. So this is summation over n is equal to 1 to n Rn cross Pn. The small n is a summation index which vary from 1 to capital N, where capital N is the total number of particles in the system, where n is 1 to n. Torque J is equal to dj by dt. That is the rate of change of angular momentum. So we can represent in summation form this expression as summation over n is equal to 1 to n Rn cross d by dt of mn v1. This is nothing but Fn, that is the forces acting on particles. In this summation, the moments of the internal forces of mutual interaction balance each other, because each pair of equal and opposite collinear forces, which is action and reaction, will have equal and opposite moments about the reference point, so that the addition of these two moments is zero. Hence, the rate of change of angular momentum of the system about any point is the sum of the torques about that point of all the external forces acting on the system. This is just as we explained in the case of conservation of linear momentum in the case of system of particles. What happens here is, when we are considering a system of particles, there are internal forces between the particles inside the system, and this appears in equal in magnitude and opposite in action. So each pair may balance each other. So the linear momentum total linear momentum will balance each other. So the total internal force, the rate of change of linear momentum may cancel each other. So the total force acting on, that is sum of total force acting on individual forces, is the external force acting on the system, appear as total external force acting on the system. That's all. This is because of the balance of the individual forces acting between pairs of particles according to Newton's third law. So this is about angular momentum, torque, and these quantities for a system of particles. Now we'll discuss about what is conservation of angular momentum. In a free particle, in a free system left to itself, the external torque tau is 0. So in a free system, the external torque acting on the system will be 0. So in that case, we can write dj by dt is equal to 0. dj by dt is nothing but torque. So torque is 0 means dj by dt is equal to 0, which means J is constant. That is, derivative of a quantity with respect to time is equal to 0. Derivative of a quantity is equal to 0 means that quantity is itself a constant. So J is constant, which means J is equal to J1 plus J2 plus etc. is a constant. Thus the total angular momentum of a system of particles is constant if the external torque acting on the system is 0. This is the principle of conservation of angular momentum. So the principle of conservation of angular momentum says that if the external torque acting on the system is 0, the total angular momentum remains constant. This is conservation of angular momentum. In the absence of external torque, total angular momentum J1 plus J2 plus etc. of the system remains constant, although the angular momentum of the particles may mutually interchange. Though they may there are individual angular momenta or may vary, the total angular momentum remains constant. This is about the conservation of angular momentum.